Hey everyone, welcome back into this virtual lecture on the cross product. In this lecture, I'd like to take a moment to tell you some properties of the cross product, some kind of theoretical properties here. So in this situation, let's let A, B, and C all be vectors in three-dimensional space. So remember, V3 is the collection of three-dimensional vectors. And let's let K be a real number. So that means K is a scalar, right? So K is a scalar in this situation. I'm going to write down some properties that some of them we've already talked about and some of them are new, and then we'll do an example with one of them. One of them has extreme geometric significance here. So first of all, let's just remind ourselves that A cross B is always perpendicular to both A and to B. And when I say perpendicular, I really mean orthogonal. A cross B is orthogonal to B as well. This is always true, right? And so the reason for this is because our definition was that, it was part of our definition, right? Our definition was that the cross product is the vector that obeys the right-hand rule for these two. There's another way to write this, right? So this means that A cross B dotted with A is always the number 0, right? And similarly with B. Remember, the dot product being 0 is the definition of orthogonality. So there's property 1, we'll call it. Property 2 is another scenario here, so that we've talked about. A cross B is equal to the 0 vector if and only if what? If A is parallel to B, or you could say that means they have the same, so the angle between them is either 0 or pi, or if either A is 0 or B is 0, of course, right? 0 crossed with anything is a 0 vector. But the key here is that A cross B for non-zero vectors A and B is equal to 0 vector if and only if those two vectors, original vectors, are parallel. So that means that their angle, the angle between them, is either 0 or it's pi. Okay? Remember, parallel it means that the line segments are parallel. It doesn't mean that they're pointing in the same direction necessarily. All right, here's some other ones. So again, just by our definition, A cross with B, by the definition using the right-hand rule, is that this has to be equal to the negative of B crossed with A. All right, so there's another one that we've talked about. That's part of our definition. Now here's a new one. Number 4 here is going to say that if we have a number K and we want to multiply this by our cross product, A cross B, remember K is a scalar, right? So K times A cross B, this is the same as K times A crossed with B, which is the same as A crossed with K times B. So in other words, we can distribute the scalar multiplication to either one of the vectors, A or B, but we have to be very careful not to change the order of the cross product itself, right? So the order of A cross B has to remain the same regardless of where we put that scalar K. All right, so the next property is a couple of different properties of the distributive property. So let's suppose that we wanted to add together two vectors, A plus B, and then cross with the vector C. And we want to try to distribute this cross product over our vector addition. It turns out we can do it, but we have to obey, once again, the order of the cross product. So this has to be A cross with C in that order, and then plus B cross with C. So the cross product can distribute over the sum, but it had to do it keeping the cross C on the right-hand side of each of the vectors that were added together, right? And similarly, we can write this. What if we had A crossed with B plus C? It's the same idea, right? We can still distribute the cross product, but now the A cross has to stay on the left of each of these vectors that it's distributing to. So this is then going to be A cross B, then plus A cross C. All right, so there's a distributive property of the cross product over vector addition. All right, there are two more properties here. This next one I'm going to put a star by because we're going to come back to this one. This is number 6. This one says that if we wanted to take A dotted with B cross C, this is the same as taking A cross B and dotting with C. All right, so this is just something that you can work out. So remember, these vectors are all three-dimensional, so you can write these out in component form, and you can work out that this is indeed true with symbolic vectors A, B, C, And I recommend that you do that. So RE, recommended exercise. Actually work that out and show that the changing of the order of the products, but leaving the three vectors in the same order, but changing the order that the products are taken, results in the same answer. Now, when you do that, be very careful, right? Because the cross product gives you a vector, right? And the dot product gives you a number. So you have to do the cross product first. That's why there's parentheses here. The cross product in either case has to be done first. All right, we're going to return to this one in a minute because that product itself has a name. The identity doesn't have a name that I know of, but the product has a name and it has some geometric meaning. But first we need to write down our last property here. And this one is that if you take the cross product of B cross C and then cross it again with a third vector, say A, and cross it on the left, remember order matters, right? So B cross C first, and then on the left cross with A, so A cross your answer. Then what you get is this property, which is very useful. So this one ends up giving you A dotted with C times B minus A dotted with B times C. All right, so remember, you take a cross product, you get back a vector. The vector you get then is a linear combination, we call it, of the difference of B and C. So B, or you can even say the sum, but this one's got to be subtracted, right? So it's a linear combination of B and C, and the coefficients are related to the dot product of A with the opposite one of them. So A dotted with C times B, that's a number, times B, minus A dotted with B times the vector C. Subtract it all out, and you get this vector identity. All right, let's go back to this number 6 here. So this product that shows up here is kind of unfortunately named. It's misnamed in some ways. But it's called the scalar triple product. So let's let A, B, and C be vectors in three-dimensional space again. So vectors in V3. The scalar triple product of these three. The part that's unfortunate is that it's not a triple product. It's a double product. There's two products here. There's three vectors though, so I think that's why it's named as it is. But the scalar triple product of A, B, and C is the number given by. So scalar indicates number, and indeed it's going to be a number, but it's going to be the number A dotted with B cross C. All right, so there's the scalar triple product. Now, why do we care about this one? Well, remember that B cross C, the length of B cross C is related to, it's not related to, it's exactly equal to the area of the parallelogram spanned by those two. So down here I'm going to draw these vectors, all right? So I'm going to say this one's B, and let's say that this is C. All right, and we know that the area of this parallelogram is the length of the cross product. We also know that the cross product is perpendicular, right? So it's perpendicular to that entire plane, actually. So this is B cross with C. And then it turns out that if A is some other vector, so this A, let's say A looks like this, then the scalar triple product here is, it equals, so I'm trying to not get too technical here, but if you were to then take this parallelogram and slide it up the vector A, then what you would do is you would fill out what's called a parallelepiped. Everything's supposed to be parallel here, so use your imagination with my drawing, right? But the idea here is that this is called a parallelepiped. All right, and this dot product of A with B cross C gives you the volume of this parallelepiped, it turns out. So the volume is very geometric, very, very important geometric fact here, right? So the volume of the parallelepiped, I'm going to really abbreviate it, PPD, parallelepiped. The volume of this parallelepiped determined by A, B, and C. So A, B, and C is given by the absolute value of this number. So the scalar triple product has got a dot product at its core here, right? So it could be negative. So we'll say V is A dotted with B cross C. absolute value because it's a volume, right? If you get a negative number, that just means that you've broken the right-hand rule somehow, but you haven't changed the volume. You've changed the orientation of your edges somehow. So let's do an example of this one, but this is, again, important product here. Scalar triple product, parallelepiped, volume of a parallelepiped. So in this example, I'm going to change the question a little bit. So this one, I'm going to give us three vectors. So let's say we have a vector A, 2, -1, 3. Vector B, this one's given by, I'm just making this up, but 2, 1, -1. And a vector C, given by 0, 1, 3. And what I want to know is not the volume of the parallelepiped. So we don't even need to know which of these vectors is which here. But I want to know the volume of the tetrahedron. All right, so the tetrahedron you get by connecting all the tips of these, and then you get this four-sided shape. Tetra means four, right? The volume of this tetrahedron is going to be what? So yeah, it's going to be half, right? This is going to be half of the scalar triple product. So it's half the volume of the parallelepiped. So 1/2 of the absolute value of A dotted with B cross C. So that's what we're going to compute here. And one of the main reasons I want to do an example of this in a video is that we can use our special, or trick basically, method of computing the determinant to help us out here. So usually when we want to do B cross C, we set up our cross product like this, right? So B cross C, I put the hat on the wrong thing. B cross C is equal to, usually it's I, J, K, right? And then we fill in the vectors. So 2, 1, -1, 0, 1, 3. All right, but it turns out that if we want to then dot this thing with A, then actually what we can do is we can go through and erase the first row, and we can input the components of A right here and do the same exact process that we did before, except now we're going to get a number back, right? And that number is going to be exactly the volume that we want. So I am going to do my copy paste method here to extend 2 more rows, or 2 more columns. So these 2 columns. And then remember, in terms of our trick, our kind of fancy method here, we multiply these diagonals. Just make sure you get the right terms to multiply. Multiply those, add them up. And then I've got the wrong color here, then we multiply these ones and subtract, right? And this right here is going to give us the volume of the, maybe negative, right? But the volume of the tetrahedron we'll still have to divide by 2. But this is going to give us what? It's going to be 2 times 1 times 3. So 6 plus, this is 0, plus 6. And then we subtract these off, right? So I'm going to do a big subtraction. So this one is going to be -6. This one's going to be -2, and this one's going to be 0. All right, and so what we have here is 6 plus 0 plus 6 plus 6 plus 2 plus 0, and this is 20. All right, so that's the volume of the tetrahedron. The parallelepiped. I think I misspoke a minute ago. This is the volume of the parallelepiped, right? And so the volume of the tetrahedron is half of this, right? It's 10. Okay, so we'll leave this video here.